Interrupts of 8051. To interface input-output devices to microcontroller, two methods are available. The first method is polling method and second method is interrupt method. Now let us understand polling method. In polling method, when we want to interface IO devices to microcontroller, suppose these are IO devices, IO device 1, 2, 3 and n number of IO devices we want to interface to microcontroller, then every time microcontroller has to check whether device is ready or not. So here first it is checking the first IO device. If it wants a service from microcontroller, then microcontroller will provide a service to this IO device. That means it executes service routine or program written for this IO device. If it does not want any service, then microcontroller will check next device. Then again it will go to next device. So if n number of devices are available, n time microcontroller has to check these devices. Suppose there are 100 devices, then microcontroller has to check all these 100 devices one by one whether they are ready or not. So this method is time consuming, and because of this the polling method is not used when number of input output devices are more. Instead of this, the interrupt method is used. In interrupt method, whenever device is ready, it sends a signal to microcontroller and then microcontroller will execute service routine, that is program written for this particular IO device, that is called ISR, interrupt service routine program. So microcontroller can do its own work, and whenever any device is ready, it sends a signal to microcontroller and microcontroller provides the service to that particular interrupt. So it saves the time of microcontroller. For example, we can take a real time example or our daily life example. The polling is same as the salesman selling its product by going door to door. So it has to go to each house and sell his product, while the shopkeeper is sitting in his shop, and whenever the customer want to buy anything, they went to shop and buy the thing. So this is the main difference between polling method and interrupt method, where in polling method microcontroller is going to check a device, and in interrupt method whenever device is ready it sends a signal to microcontroller. Now in 8051, six types of interrupts are available. The first interrupt is reset interrupt. Reset interrupt is hardware interrupt. There are two types of interrupts, hardware interrupt and software interrupt. Reset interrupt is hardware interrupt because microcontroller has a reset pin, and whenever the signal is given to this reset terminal, it resets the microcontroller and start executing program from address 0000H. The second is timer zero overflow interrupt. So that is TF0 interrupt. Third is timer 1 overflow interrupt, TF1 interrupt. These both interrupts are software interrupts. Software interrupts are interrupts generated by internal blocks of microcontroller. So timer is internal block. So these two interrupt, these are the flag bits, and whenever timer work is over, microcontroller sets this flag bit to 1 and it gets an interrupt signal. Then external hardware interrupt INT 0. So this is again a hardware pin of microcontroller, that is pin number 12, P3.2 pin of microcontroller is used as a external hardware interrupt 0 pin. External hardware interrupt 1 pin, that is INT1, that is pin number 13, P3.3, it is the second hardware pin. And the sixth interrupt is for serial communication interrupt. It is again a software interrupt. For both receiver and transmitter, only one interrupt is used. So RI is the flag bit used for receiver and TI is the flag bit used for transmission. So these are the six interrupts available in the 8051 microcontroller. Now, as I have told that each interrupt is having its own program that is called as a interrupt service routine program. So each interrupt service routine program has a fixed address. So reset is 000H, that we know. Whenever we reset a microcontroller, will give a signal at reset pin. Microcontroller start executing program from 000H address. So here we can say that at this address the program is written which will be executed after getting interrupt on reset pin. The second is timer 0 overflow interrupt IF0. The program written for this interrupt should start from 000BH address. That means after receiving this interrupt, microcontroller will execute a program written at this address 000BH. Same for timer 1 overflow interrupt, that is TF1, address is 001BH. So here we have to write interrupt service routine for timer 1 interrupt. The next is external hardware interrupt INT0 whose address is 0003H. The next interrupt is external hardware interrupt INT1, that is pin 13 P3.3 and address is 0013H. The address for serial communication interrupt is 0023H. So for reception or transmission interrupt, we have to execute a program written at address 003H. So these are the addresses of interrupt service routine for particular interrupt. So while writing a program for interrupt, we have to use these addresses. So these are the addresses. Then priorities of interrupt. Suppose two interrupts occur simultaneously, then how microcontroller provides service to these interrupts or which program microcontroller will execute. So for that the priorities are given. So microcontroller will always execute a program or interrupt service routine written for higher priority interrupt. So reset is having highest priority. So whatever microcontroller is doing, but if there is a signal at reset pin, it has to provide service. It has to execute a program written at this address location of this interrupt, that is 000H. External interrupt INT0 is having a priority 1. Timer 0 interrupt is having priority 2. External interrupt 1 is having priority 3. Timer 1 interrupt is having priority 4 and serial communication interrupt is having lowest priority, that is priority 5. So if more than one interrupt occurs simultaneously, microcontroller provides service to interrupt according to their priorities. Register for interrupt. The first register is interrupt enable register, that is IE register. It is 8-bit register. The MSB bit is enable bit. This should be set to 1 for any interrupt if we want to use in our program. So EA bit should be always 1. So it is used to enable or disable interrupt. To enable interrupt, this must be 1. These next two bits are reserved bits, so we can store here 0. These are the individual bits which can be used to enable or disable individual interrupt. For example, ES bit is used to enable or disable serial port interrupt. So whenever you want to enable this interrupt, this bit should be set to 1. We are going to see the example of timer 0 interrupt. So when you are using timer 0 interrupt, no need to enable this bit and this bit should be 0. The next bit is for timer 1 overflow interrupt. So when we want to use timer 1 interrupt, this bit should be 1. Otherwise, should be 0. The next is external interrupt 1. So when we want to use it, this bit should be 1, otherwise it is 0. ET0 bit is used for timer 0 overflow interrupt. So we are going to say the example of timer 0 interrupt. So we'll set this bit to 1 so that timer 0 interrupt will be enabled. The next bit is for external interrupt 0. So when we want to use external interrupt 0, that should be 1, otherwise it is 0. Now this we can convert it into hex, and that should be stored in IE register. So if we convert it into hex, we'll get a value 82H. So 82H should be stored in IE register. We can use immediate addressing mode of move instruction. So this is the IE register. The next register is interrupt priority register. Now by default the priorities of interrupts are fixed. Like reset is having highest priority and we cannot change the priority of reset interrupt. But we can change the priority of other interrupt. So priority of one interrupt at a time can be changed by the user, and for that this IP register is used. These are the bits for each of this interrupt. As we know, the highest priority is given to external interrupt. But suppose I want to give highest priority to timer 0 interrupt. So for that the bit used is PT0. So PT0, if we set to 1, all other bits should be 0 at this time. It indicates that the highest priority is given to timer 0 interrupt. So microcontroller will first provide a service to timer 0 interrupt, and then it will go according to the default priorities of interrupt. So priority of one interrupt can be changed, and it is required when more than one interrupts occurs simultaneously. Then only microcontroller will go as per their priorities. So even if now hardware interrupt and this software interrupt, that is timer 0 interrupt, occurs simultaneously, first microcontroller will provide service to timer 0 interrupt, and then it will go for the other interrupts as per the default priority. So this IP register also we can initialize at the starting of our program so that microcontroller will come to know the priority of the interrupt. So we have to convert this data into hex, and that will be stored in the IP register. So it is used only if we want to change the priority of interrupt. Otherwise, we can use the default priorities set for the 8051. Let us understand how microcontroller provides service to interrupts. Suppose this is the main program and three instructions are written in the main program. So microcontroller will execute this instruction, but while executing the instruction, if any interrupt occurs, then microcontroller will complete the execution of instruction first. For example, suppose it is executing this instruction which is written at address 0002H, and since it is 2-byte instruction, it requires this 2 memory location, and after fetching this instruction, contents of program counter will be 0004H. So while executing this instruction, suppose interrupt occurs, then microcontroller completes the execution of this instruction. It will execute the instruction and then it executes instruction push PC. So that means it stores the address of next instruction on stack memory. So here the stack memory is shown. First microcontroller is supposed pointing to this memory location. So after execution of this instruction, it will increment stack pointer by 1. It stores the value of lower bytes of program counter that is 04H in this case, and again it will increment stack pointer by 1 and store the value of higher bytes of program counter, that is 00H. So it will save the address of next instruction on stack pointer. After that, it will store the address of ISR of interrupt in program counter. Suppose it is timer 0 interrupt, then fixed address for ISR of timer 0 is 000BH, so that will be stored in program counter. So since 000BH is stored in program counter, microcontroller will start executing instructions written at this address, that is ISR. So suppose we are writing this ISR with this assembler directive, and these are the instructions written in ISR of this particular interrupt. So it will execute this instruction. Now the last instruction of ISR must be return instruction, that is return from interrupt, RETI. So while executing this instruction, microcontroller execute pop PC instruction. That means the address of this instruction, which is stored on stack memory, will be stored back into program counter. So 0004H will be stored in program counter and microcontroller will start executing this instruction and then the other instruction sequentially. So this return instruction is to return back to main program. So operation is same as a call instruction and return instruction, but here this address is fixed for each interrupt, and the last instruction should be RETI, not only RET instruction. So this is how microcontroller executes the interrupt. Now we'll see the example of timer 0 interrupt. So timer 0 interrupt means TF0 for timer 0 and TF1 for timer 1 flag bits are used as an interrupt. Now how we'll write this program? So just go through the steps for main program writing. So first we have to configure tmod register. We have already discussed about format of tmod register. Then next is enable IE register. That means decide which interrupt you want to use and enable that particular bit. Next is initialize this count register. So as per the delay, we have to initialize TL and TH registers. And then we'll start a timer. Now while this timer is counting, microcontroller can do any other work. We can assign any work to microcontroller, and whenever interrupt occurs, it will go to interrupt service routine, return for that particular interrupt. For ISR, we have to first write a similar directive, that is org, and here we have to specify address of ISR. And then we can write the instruction as per the statement given or as per the application. After executing these instructions of ISR, stop the timer, clear the flag bit. Actually, interrupt also clears this flag bit, so we can avoid this. Then load again the count register for next operation and start the timer, and then return back to main program. So it will return back to main program and start executing instructions of main program. So let us see how to write a program using this timer 0 interrupt. So we'll write a program to flash LEDs which are connected to port 2, and will flash these LEDs with delay of 10 milliseconds. While doing this, this timer has given, or a microcontroller has given one other work, that is read a data from port 0 continuously and send it to port 1. So continuously microcontroller will do this work, and when interrupt occur, it will change the data of port 2 to make this LEDs on and off. So we have to use here timer 0 in mode 1 and interrupt of this timer 1 to generate a delay. So this is the circuit diagram. To port 2, 8 LEDs are connected. We want to flash this LED. When we'll send logic 1 here, the particular LED will glow, and when we'll send logic 0, the LED will turn off. While doing this, we want to read a data from port 0 as an input port and then write a data to port P1. So this work microcontroller should do continuously. So for this, we'll write a program. So we'll start writing a program from address 000H. So we'll initialize, first step is to initialize tmod register with value 01H. We are using timer 0 in mode 1. Then we'll load a count. This count is for a 10 millisecond delay. So you have to write here later H. So hex data will store in TH0 and TL0. Then we'll initialize IE register with 82H, that is timer 0 interrupt is enabled. On port P2, 00H is stored. That means all LEDs of port 2 are turned off. Accumulator also I am sending or initializing with value 0. Then we'll start a timer 0. So for that we are using set bit tcon.4. Now timer has started and it started the counting. But till interrupt occurs, that means till TF0 is 1, you can assign other tasks to microcontroller. So we'll read a data from port P0 that is stored in accumulator and we'll send the data of accumulator on port P1. Here, one thing you have to remember that we are using port P0 as an input port. So whenever we want to use any port as an input port, you have to send FFH to input port. This is used to save this port. Otherwise, the port will be damaged. That we'll discuss in another lecture, or you can watch the video of internal architecture of ports. So port 0 is input port. So for that we have to initialize it with FFH and then we can use it as an input port. Read a data from port P0, store it in accumulator and send the accumulator data on port P1. S jump back. So continuously it will execute these instructions, but whenever interrupt occurs, it will go to the address 000BH, which is the address of ISR routine of timer 0. So here we'll first stop the timer because our work is over. We'll clear the flag bit. We'll complement the accumulator. So 00H becomes FFH and this FFH data will send it on port P2. So directly we cannot complement any register. So we'll complement accumulator and send it this data on port P2. So again for next cycle, we'll load a count in count register and then we'll start a timer. So timer started, but till the timer completes its operation, we can do this work. Microcontroller can do this work. So it will return back to the instruction from where it has gone to this ISR routine. So this is how the program can be written for this interrupt of timer 0. Now here problem is that we are writing our program from address 000H. So our program may be large and this program start from address 00BH. So there may be a overlapping of this main program with this ISR program. So if there is a overlapping, our program cannot be executed properly because maybe this instruction is written at this address 00BH and we are writing these instructions also at the same address. So to avoid this overlapping, what modifications we can do? So this addresses are given and because of this there can be overlapping between our main program and the ISR program. So to avoid this, what we'll do at this 000H where microcontroller is going to start, will write instruction ljump main. So when microcontroller will execute this instruction, this is 3-byte instruction. So it requires 3 memory locations 000h, 0001h and 0002h. So there can be a overlapping. So whenever microcontroller execute this instruction, it will jump to main label, and in main label we'll write our main program. So after this we'll write the ISR routine program from address 000BH. The same program is written here, that is ISR program, and main program will write with label main. So the same main program is written here. So whenever microcontroller will execute this instruction, it will first jump to main label, it will execute these instructions, and whenever interrupt occurs, it will go to this ISR program. So this main label program we can write after writing this ISR routine, or you can mention org assembler directive also for main program. So I have written here address 1000h, so there won't be any overlapping between this ISR routine program and our main program 1000h, or you can give this choice to microcontroller. So just write main program after completing this ISR program. So this is how we can write programs using interrupts or of timer. Same you can use for other interrupts also, for timer 1 interrupt, for our hardware interrupts, like that.